So most of the elements on the periodic table we're going to describe as metals. And metals, that's a word that you know. I mean, you kind of know what a metal is. And a metal's different from a non-metal because metals have certain properties in common. Right? Metals tend to be hard, they tend to be shiny, they tend to conduct electricity, and things like these properties of metals we can actually understand on the basis of band theory. Again, this is one reason why if you want to change a property of a metal, for instance, how do you do that? Well, you could just trial and error and guess, so you can actually understand what's going on at the electron level, which is what we're trying to do here, and understand why metals are what they are, and how to perhaps control their properties, and how to predict what their properties might be. So let's do that. Let's use band theory to explain some of the properties of metals and see how it all works out. And so, for instance, metals tend to conduct electricity, and this is something we can understand on the basis of band theory. Again, we're going to go back to lithium as an example again. It's our sort of favorite example. And lithium metal, of course, has this band structure. It has the 1s band, and because the electronic configuration of lithium is 1s2, 2s1, 1s2, this band is filled with electrons, completely filled with electrons, whereas the 2s band isn't, because there was only one electron in the original 1s atomic orbital. For each lithium atom, there's one electron in the 2s orbital per atom. So what that means is the 2s band is only half filled, and we already talked about that. So for a metal to conduct electricity, there has to be something to drive the electrons through the metal. And conduction of electricity means electrons moving through the material in response to something, in response to different electron energies. But that really means some kind of electrical potential. So you can do this different ways. You can hook up a battery to a battery to the end of the different ends of the battery to different ends of a wire made out of this metal, for instance. And when you do that, that changes the energy electrons at different ends of the wire, for instance. And for instance, if you did this with a battery and you have a positive, for instance, a positive potential at that end and a negative potential at that end, the electrons get attracted towards the positive, the positive potential end. And to do that, they have to move through the metal. They literally have to move. So for the electrons to move, they need to find a different orbital, because once they need to go into a different orbital to actually relocate themselves. So remember, orbitals can only hold 2 electrons at a time, but to move, they need to find an empty orbital, and this empty orbital needs to be very close in energy, and it is. And so, for instance, there's a very, very, very large number of empty orbitals right here, just above where the electrons actually are. So it's very easy for the electrons to find an empty orbital, and in doing so, move through the metal. The electrons will literally move using those empty orbitals as like a little highway, if you like, to actually move. If we apply a charge across the electrons of the 2s band, at the same time we're applying a charge across the electrons in the 1s band, and in this case there's no change in the electron position because all the orbitals are full. So if there are no empty orbitals, there's nowhere for the electrons in the 1s band to go. They can't move. So we just learned a lot of things. We learned why metals tend to be conductive, and we also learned which electrons are the ones that move when the element actually conducts electricity. So these are the electrons that move, the electrons in a band, and so they have to be in a band which has some empty orbitals in it, and bands which have empty orbitals in them which will allow electrons to move in this way. These are called conduction bands. And so the conduction band for lithium metal is the 2s band, because that's the band where the empty orbitals are. So in other words, you can only get this when you have this metallic bonding. We have these orbitals so close together, and you can also only get it in a band which actually has empty orbitals in it. We're going to talk more about conduction in different parts of the course, but fundamentally, this is what's going on. And this is the best way to explain conduction. Again, this is an example where looking at the material through atomic level is actually beneficial. It wins. Metals are also malleable, and that means you can change their shape. You can bend some metal and it won't break, and so you can move and you can sort of beat on it, you can make shapes out of it. And the reason for this is because if you move the atoms in a metal, then you don't really change the bonding. So let's imagine we have some metal here. Imagine we have some lithium metal. And we're showing just a small part of all the atoms and have this disarrangement. If we actually bend the material, then atoms are going to have to move. So let's imagine that all these atoms have to move this way and these atoms move this way and so on. After they've moved, each atom is still making exactly the same number and the same type of bonds that it was before. So you can move the atoms one with respect to each other and the bonding doesn't change at all. So the atomic orbital overlap is the same when we move the metal. Now, you can't do that with other types of material. Because the bonding is identical, that allows you to physically change the shape of the metal. Another property of metals is their so-called luster. And what luster means shininess. And a material is shiny when light hits it, it reflects off it, kind of like a mirror. And none of the light's absorbed. And a material is shiny when it reflects all light wavelengths and energies equally. In other words, there's no color. And this is understood, and metals, of course, do this, you're aware of this. This is actually more of a physics phenomenon than a chemical phenomenon, but we should talk about it anyway because we've just described chemically what the physics relies on. And again, it relies on band structure, and it involves electrons that are easily movable. And we just decided that electrons are easily movable in a band, particularly a band which has empty orbitals, such as the 2s band in lithium. And so electrons can move from one orbital to another with almost no energy cost. And this is the property that accounts for the conductivity, also accounts for the reactivity of the so-called luster. So here's the idea. Let's imagine we have some light beam coming in, and the light beam consists of an oscillating electric and magnetic field vector. And so let's imagine the electric field vector oscillates something kind of like this. So here's the light beam coming in. When it comes in, the electric field vector is oscillating up and down very quickly, and that can cause the actual electrons in the material also to oscillate very quickly. And they can do this because of this empty orbital, this band structure. The electrons start to oscillate very quickly. Now, when the electrons start to oscillate, when they're moving, they also emit radiation. It turns out it's completely out of phase of the input radiation. That's a detail we won't ask you about. And so this is the light energy that comes out. And the light energy which comes out at the same angle that it went in at turns out to be, that's the energy where the light energy come out is least likely to suffer destructive interference, which is why basically the light comes out at exactly the same angle that was incident upon the piece of metal in the first place. So the incoming electric field vector induces oscillations in the polarizable electrons. Polarizable electrons are those which can move very easily. Electrons which can move very easily in a band structure are said to be polarizable, and that results in light being very rapidly emitted at the same time. Really, in all honesty, this is physics, and so if you really want to learn a lot more about it, there's a beautiful book by Feynman, which is quite easy to read. I suggest you go and read that one. But fundamentally, the physics behind this depends upon the chemical description of what the electrons are doing in terms of band structure. So band structure helps us understand all of the usual properties of metals that you already know about.